The reliability of any estimator is determined by the variance and the standard error or standard deviation of that estimator. Here beta 2 hat is the OLS estimator, and a measure of its reliance would be how high or low the standard error of this estimate is. So let us now derive the formula for the standard error of beta 2 hat. We can begin with the formula for variance of beta 2. If you remember, the variance of any variable is the mean of the square of deviations around its mean. What I mean is, variance of beta 2 hat would be the mean of its beta 2 hat whole squared. This is the formula for variance. Expectation of beta 2 hat minus expectation beta 2 hat. Here expectation of beta 2 hat is the mean of beta 2 hat. So deviation from the mean squared, the mean of deviations from the mean squared is the variance. So taking the expectations, taking the unbiasedness property into consideration, which says that expectation of the OLS estimator or the mean value of beta 2 hat is equal to the true population parameter beta 2. We can write variance of beta 2 hat as equal to expectation of beta 2 hat minus the population beta 2 parameter whole squared. Now, if you remember from our earlier proof where we were showing how beta 2 hat, the mean value of beta 2 hat is unbiased estimator of population beta 2, we had shown that beta 2 hat is equal to population parameter beta 2 plus summation ki ui. So I'm using this relationship to substitute this term. So I'm writing variance of beta 2 hat is equal to expectation of summation ki ui whole square. Summation ki ui whole square can be expanded in this form. K1 square u1 square plus K2 square u2 square etc. plus Kn square un square plus 2 times K1, K2, U1, U2, etc. I'm continuing it in the last line, etc. plus 2 times Kn minus 1, Kn, Un minus 1, Un, and so on. Here I have used the general expansion of a plus b whole square, general formula for a plus b whole square, when it is expanded to have many terms. Now, again, we will make use of the assumptions of the classical linear regression model. We are using two main assumptions. One is that of homoscedasticity, which said that the variance of the error term or expectation ui square is sigma square, constant irrespective of the value of x that we are considering, and also another important assumption of no autocorrelation, which was symbolically represented as expectation ui, uj is equal to 0 for all I not equal to j. Using these two assumptions of the classical linear regression model, I can reduce all such interaction terms where we have u1, u2, u2, u3, un minus 1 un. All of these interaction terms will become equal to 0 when we take the expectation. So what we are left with is expectation of the terms k1 square u1 square plus k2 square u2 square and so on till kn square un square. And we know that since the variables k1, k2, kn are all made up of non-stochastic x variables, the expectation can only be taken for the terms u1 square, u2 square, u3 square and so on till un square. So, making use of the assumption of homoscedasticity, I can say that the variance of beta 2 hat is equal to sigma square times summation ki. Remember, all these terms where u1, u2 and uj are interacting, when I took the expectation it became equal to 0 because of this no autocorrelation assumption. Now again, sorry, there's a square here. Now again, from the properties of ki that I had discussed, if you remember, I had shown how summation of ki square is nothing but 1 by summation xi whole square. So using this, I can write variance of beta 2 hat as equal to sigma square divided by summation xi square. The standard error is nothing but the square root of the variance. So it will be the standard error, if I may write it here, the standard error of beta 2 hat is equal to square root of sigma square by summation xi whole square. In other words, it will be sigma divided by square root of summation xi whole square. This is a very important relation which we'll keep using later on. And also to prove that this OLS estimator beta 2 hat is the most efficient or has the minimum variance in the entire class of linear unbiased estimators.